Hello, and welcome to one of 8 short videos from Skills for STEM. Each video is designed to supplement your CIOB Chartered Membership Program workbooks. These videos should be studied in conjunction with each of the 4 modules, and you should also undertake further reading on the topics introduced. This will help to improve your overall knowledge. The videos will also introduce some useful websites which you can refer to help you to gain a better understanding of the subject. Feel free to stop and start the videos and to make notes in the margins of your workbooks to help you. If you are unsure of a topic, you can always watch the video again to help your learning. Good luck in your pursuit of Chartered Construction Manager. Module 1, Construction Technology, Part 1. The introduction of soil engineering is a relatively new discipline. Prior to this, buildings tended to be constructed with little by way of foundation engineering, and this was true up until about the 1880s. When buildings of 12 stories or more became more prevalent within New York and Chicago, the main consideration for foundation engineers was not to avoid settlement, as this was considered inevitable, but to ensure that each foundation settled at the same rate and ultimately by the same amount. Engineering substructure works form an essential part of buildings, whether they are for rail, road, office, or private dwellings. Ground and substructure works undertaken to prepare the site for the proposed structure create foundations necessary for its support. Most local authorities expect desk-based and ground investigations of the site once planning permission has been granted. These include all investigations like the identification of abandoned mine works or industrial activity or other geological anomalies. Tests will also be conducted to determine if there is any contamination, and the makeup and density of the ground will also be established. Based on the information contained within the ground investigation report, a foundation or structural engineer will then specify requirements for the foundations for any proposed structure. The foundations will depend on ground conditions identified at site, and they should be identified within the investigation report. It may be that shallow concrete foundations, such as a strip footing or pad foundation, are specified, but that would only be if the soil is relatively stable. For less dense or unstable soils, reinforced concrete raft foundations may be considered for lightly loaded buildings. For more heavily loaded buildings, it may be necessary to undergo ground improvement solutions, such as vibrocompaction. This can help to bond loose sands and gravel and increase their load-bearing capacity. For very large buildings, where high loads are experienced, it is necessary to apply more heavy-duty solutions, such as driven piles. These will help to support the weight of the building and reduce settlement. Deep foundation solutions require piles to be sunk until they reach more stable ground beneath the structure. These could be calcium piles, for example, which are used for the construction of bridges. There are a number of different piles and piling techniques that can be used to create the foundations. It really does depend on what is being built. A piling contractor will recommend pile types that could be employed to sink the required number of piles. They will often use CFA or continuous fly auger piles. These are formed by first drilling a hole and then filling the hole with a steel reinforcement cage and concrete. An alternative to this are driven piles, which may be used with softer soils and sit above more stable rock. These techniques involve driving a precast concrete pile or steel tube into the ground with a hydraulic hammer until eventually it meets the required resistance. Driven piles are a form of displacement piling, as the soil is moved out of the way as the pile is driven into the ground. As a result, in this technique, no soil is removed. Piles can also be used to provide stability, for example, on sloping sites where there is a requirement for a retaining wall. To stabilize soil, the driving of sheet piles, or steel sheeting, creates a solid solution. Due to the increase of land and its relative availability, There has been an increase in the number of home owners creating what have been known as iceberg houses. These are where the construction of basements is added underneath the building itself in order to potentially triple the size of the property, for example. The creation of this new habitable basement will require building regulation approval, regardless of whether or not it changes the use of the existing cellar. It also requires that the statutory minimum construction standards are also complied with. The Basement Information Centre provides reference material on how to apply the building regulations appropriately. More recently, some local authorities have taken to requiring full planning application prior to the construction of habitable basement spaces. It is important to note that if the proposed works impinge on a party wall, i.e. if there are any impact on the party wall or properties adjacent, it is essential to follow the relevant legislation, which is the Party Wall Etc. Act 1996. This can be found at the legislation.gov.uk's website. In order for a basement to be successful, it needs to be appropriately waterproofed. British Standard 8102 defines the protection of below ground structures. It defines the grades for basement use. Grade 1, basic utility for car parks, plant rooms, but not those including electrical equipment. Grade 2, greater than basic utility, workshops and plant rooms requiring drier environments than those in Grade 1, which is where you would install electrical equipment, for example. Grade 3 as habitable, ventilated residential and commercial areas. And finally, Grade 4. This is a special area required for archives and other controlled environments where you would need a drier condition. The Basement Information website gives a lot of information on the construction of basement areas, including information regarding waterproofing below ground level, often referred to as tanking. This is achieved by using several layers of waterproof render and tying it into a waterproof screed on the floor. An alternative to this is cavity drainage, which uses a membrane embedded within the cavity. By constantly draining away any small leaks, there is never any water pressure against the inner structure, and this is considered to be the most reliable way of waterproofing a basement. British Standard 8102 also defines three types of water-resistant construction: barrier membrane protection, structural integrity protection using multiple layers of waterproof render, and drained protection. You can see examples of these on the slide on the screen. It is important when considering the various forms of construction to achieve the levels of water tightness and also consider specific vapor expulsion methods. Depending on the environment, active precautions, i.e. heating, ventilating systems and such, are typically considered as necessary. Temporary works is the term used for an engineering solution to support or protect either an external structure or permanent works during construction. Temporary works may also be used to support an item of plant or equipment or the vertical sides or slopes of an excavation during construction operations, or on site to provide access. Temporary works may be removed or left in place after completion of the project, but in this case they would not normally contribute to the strength of the permanent works. One of the main objectives in any method of work should be to minimise risk. As a consequence, British Standard 5975 provides guidance for temporary works procedures and the permissible stress designs for false works. The British Standard includes guidelines on the design, specification, construction, and use and dismantling of false works, and is explained in a clear and easy to use series of sections. The standard looks at all elements that should be taken into consideration when erecting structural systems and building structural designs. By implementing these principles, You'll be better prepared for site investigations, and it will be significantly easier to comply with the current legislation. The Leaning Tower of Pisa is perhaps the most well-known architectural oddity in the world. The construction of the tower occurred in 3 phases, taking nearly 2 centuries, mainly because of war and social unrest, which impacted on the construction. Problems with the tower were first noticed during the initial phases of construction, which began in 1173 AD. Engineers tried to compensate for the tilt by making the columns and arches of the 3rd story significantly taller on the sinking side. But political unrest halted construction again, and they could not continue onto the 4th story. Additional adjustments were attempted on the 5th and 6th stories, but construction was once again halted before they could continue to the 7th. By the time they came to conclude the tower in 1372, the builders made a final attempt to compensate for the leaning by angling the 8th bell tower section even further towards the non-leaning side. Regardless of these attempts to correct for the leaning, the tilt continued to worsen throughout the centuries. It wasn't really until 1911 that proper monitoring began. The measurements revealed that the top of the tower was actually moving at a rate of about 0.05 inches per year. One of the positives from the repeated delays in the construction was that the soil was allowed to settle during the time that each construction phase was halted. Had that not been the case, then it may well have been that the tower would have toppled before completion. It wasn't until 2001 that the proper cause of the tilt was fully understood. This was after a number of serious stabilisation efforts, which began in the 1990s, had finally been completed. It was known that before the stabilisation efforts, the tower had been built on top of an inadequate foundation, which was only 3 metres thick. It was also constructed on very soft, silty soil. If these had been the only factors, then uniform settlement of the tower could have been expected, and the tower would probably have remained in its current state. But the 800-year-old mystery was finally resolved when a geotechnical engineer discovered the primary cause of the tilt was a fluctuating water table on the north side, which caused the tower's characteristic lurch to the south side. Early attempts in 1935, when engineers tried to seal the base of the tower by drilling a network of holes into the foundations and filling them with cement, only worsened the problem by slightly increasing the lean. This failed attempt did in fact cause greater caution in approaches by future preservation teams. In the 1990s, the tower was closed to the public, as were apartments and houses in the path of the tower as a safety measure. When a specialist team was brought together in order to attempt to halt the tilt of the tower, the citizens were very concerned as they wanted the tilt to remain due to the role that it played in promoting tourism to Pisa. The preservation team took action in 1992 when the first story was braced with steel cables to relieve the strain on the crumbling masonry. In 1993, 600 tons of lead was stacked around the base of the north side of the tower to counterweight the leaning. The preservation team assured city officials that these were only temporary measures. The move frustrated the general public of Pisa, who viewed the measures as an eyesore and another blow to the tourism industry. In 1995, the team installed 10 underground steel anchors to physically yank the tower northwards. This only served to bring the tower closer to collapse than ever before. In an attempt to improve the stability of the soil, the water in the base of the tower was frozen. Nobody, however, took into consideration the fact that frozen water expands. Eventually, it was agreed that soil extraction was the only viable solution. It had the advantage of not touching the tower itself, and the process involved the installation of helical drills and after 77 tons of soil had been removed, the tower straightened by 44 centimetres, returning it to the angle it was at in 1838. What's more, the soil extraction programme reduced the stress on the vulnerable first story. The team estimate that it will take approximately 200 years to get back to its pre-stabilisation inclination. The tower was reopened to the public in December 2001. According to the Chartered Institution of Building Services Engineers, the cost of building services can be as much as 30 to 40% of the total project cost. Building services make a building come to life. They include the gas and electricity supply and renewable sources, heating and ventilation, water drainage and plumbing, escalators, lifts, lighting, communications, security fire detection, and even facade engineering. It is building services engineers that will have designed, installed and maintained those systems to keep them in working order. The key principle behind the successful installation and operation of building services begins by following the process of design, install and then maintain. These three key stages break down further into stages which are aligned to the Royal Institute of British Architects, or RIBA, plan of work. Building services design engineers play a central role in contributing to the design of the building, not only in terms of overall strategies, but also through the location of major plant and equipment, the position of service risers, distribution of horizontal surface drainage, lighting and acoustics. This means that the building services designs are often integrated into the overall design of the building from a very early stage. Increasingly, building services engineers are central to the design and specification of suitable systems, assessing the life cycle of buildings and their component parts at the pre-construction stage. A series of specific calculation and output documentation is produced based on the architect's layouts and other available information. This will include things such as cable sizing, pipe sizing, and other equipment sizing selection processes. All of these calculations and outputs are translated into drawings by CAD technicians, or more recently, by Building Information Modelling, or BIM, technicians. Many contracts for smaller buildings may procure the building services design in a design and build style of procurement, often known as turnkey. Once on site, the installer should progress the design information from the tender stage. This is often done by using a series of installation drawings, and the sequence of drawing production is shown in the Building Services Research and Information Association, or BISRIA, BG6 diagram. The building services installer should provide the client builder or the main contractor with the dimensioned installation drawings developed from the detailed design layouts. Completion of the building services installation or systems should be tested and commissioned in accordance with SIBSI commissioning codes and building regulation requirements also. Adequate time allowance within the works programme is extremely important with regards to the commissioning period, which can take several months on larger projects. According to SIBSI, there are around 61,000 firms in the sector, often referred to as M&E contractors. Of the 61,000, there are estimated to be 3,000 design consultancies. The remainder are mostly manufacturers and contractors ranging from multinational companies down to small businesses. The building services sector carries out approximately £20 billion worth of work each year, which is equivalent to roughly 3% of the UK's gross national product. The Milan Bosco Verticale, or vertical forest, is both impressive and effective. By using the trees and shrubs to provide shading during the summer to avoid solar gain, and in the winter allowing light and heat access once the leaves of the trees have fallen. This simple concept cuts the energy consumption while providing a green space in the city centre. But it's the clever use of the large aquifer under the city as a thermal store linked to heat pump technology that helps to balance the heating and cooling demands. The building services engineer on the project specified 2 heat pump units that supply 556 kilowatts of cooling and 589 kilowatts of heating. The system is split so that heating and cooling can be provided at the same time, thereby allowing apartments to be cooled on the south-facing side at the same time as they are heated on the north-facing side. The heat pumps are most effective during the autumn and spring, and heat rejected from one area of an apartment can be used to heat a cooler room. This vastly improves the coefficient of performance of the heat pumps themselves. To provide heating to manage hot water demand, there are 2 small gas-fired boilers. These maintain the domestic water temperature above the pasteurization level to kill off Legionella growth. Reflecting on the specification of Legionella prevention, the building services engineer has stated that the use of domestic water heating pump units offering temperatures of 45 degrees, together with chemical dosing, would probably have been a cheaper option. An alternative would be to use an additional heat pump to boost water temperatures to 65 degrees as an instantaneous water supply solution. This would have removed the need for hot water storage and hence the need to continuously pasteurize the domestic water supply. Irrespective of the developments in design, heat pumps still provide water at 45 degrees and the gas boilers only need to add heat to 65 degrees, meaning they work less hard. Continuous monitoring of the system helps identify areas where improvement in energy efficiency are possible. The facilities managers are able to access performance data, and the use of heat meters allow the monitoring of heat in tenants' properties and intervention to optimize the operation of the system in real time. The cost savings in energy go some way to help residents pay for the cost of pruning the trees and shrubs. It is, however, the innovative use of the HVAC system in conjunction with the vegetation that produces savings of about 35% over normal buildings of similar size. As we come to the end of this first video, it should be remembered that as a CIOB member, you are entitled to access the library of information held by the Institute. By visiting the CIOB library website, it is possible to gain details and view a number of relevant publications. This concludes the first part of this module. Thank you for watching and listening.